first time. I should say I was right. The solutions were right the first time. Don't start here. If you start here, this would be, let's just rewrite this. Negative RF.
I just go home and fast forward.
Now at this point I need to plug in the omegas. So if I go S squared divided by omega low pass, omega high pass, plus S times 1 over omega low pass plus 1 over omega high pass. Plus 1. Still good? Yeah, then you can break it down into that. And then you can break it down into that denominator. Like he said. So basically you don't actually go about expanding it, right? Yeah, if you were to keep it like this, if you actually start up here, it would probably be the easiest point, right? Because then you'd end up with it in that three-factor form. Okay. Alright, so that's one way to do it here, or you can start actually right here plugging in your omegas. Here's what I would recommend. To be not concerned about this problem, work through this one again by hand. And I would say, if you're able to identify visually a high pass, a low pass, a band pass, and a band reject, then you're 90% of the way there. Okay? So here's what you need to know. You need to know your basic op-amp inverting configuration, the Zs, right? You need to know that. You need to be able to identify those 4 basic configurations. Remembering that band reject would always have more than one op-amp the way that we're doing things here. And then the rest of the question will probably feel pretty similar to other ones you could practice with. Alright, let's keep going anyways. So we'll use the correct version, which is actually what we originally had here. So I apologize about my inability to do algebra.
It's okay, it's only being recorded.
I'm here on my own time, so there you go. Right. So here's the other thing I really want to point out about all these circuits. They're all going to roll off at 20 dB per decade, okay? They're all going to have a delta of 20 dB per decade. So this third criteria here, stop band gain roll off 20 dB per decade, that's the only way we know how to design things using these first order and second order filters, okay? If I wanted more than 20 dB per decade, I'd have to have a bunch of these back to back. So if I had a bunch of these similar ones back to back, then I could go from 20 dB to 40 dB to 60 dB. It'll get steeper and steeper because I'm multiplying, the roll-off multiplies it. You can think of it as being to the power of 2, then to the power of 3, then to the power of 4. And as 20 log, it goes in front and moves in front. So if I want something steeper than 20, I'm going to have to cascade a whole bunch of these back to back. That's the only way we can change that. Otherwise, it has to be 20 dB. Minimum input impedance, that tells you right away that the RI is going to have to be 10K. So let's, how do we know that? Okay, let's look at this in a second here. So what's the minimum input impedance of this thing right here? Well, this part right here, the minimum input impedance is when C is a short, right? So the minimum is when C is a short, and that occurs at very high frequencies. This is a high pass filter. That means that the minimum resistance is just going to be Ri. So this is your Zi, say your min, equals Ri. So the minimum input impedance is going to have to be 10K, so that tells us right there that Ri is 10K. Okay, so we have to select that. Now, knowing this is enough to get us started right now. What we can say is that omega high pass has to be 159 hertz, right? We know that, we already said that that's 1 over CI RI. So what we can do, we know RI, we know omega high pass, so we can solve for CI. So therefore CI equals 1 over omega high pass, RI. You plug in the numbers. Don't forget that there's a 2 pi here because we're talking about real frequency versus angular frequency. I shouldn't say real frequency. We're talking about frequency versus angular frequency. 159. So we got to throw 2 pi in front of there. That's 10K. Equals 100 nanofarads. That's why such weird frequencies were chosen, so that you end up with a nice number. So usually on a test, I actually don't know if this applies to the test, I can't remember off the top of my head. Usually on a test, if you see a really weird number given, it's so that something else works out nice. Otherwise, it just makes it really hard to mark. Now the other thing, okay, so we've got this part, we've got RF, we've got CI. We can choose RF and CF to meet that low pass frequency, right, the 1.59 megahertz. But we can't just arbitrarily choose RF, right, because we know that we need to achieve a particular passband gain. We know that we must achieve K equals -10 equals negative RF over RI. Therefore, RF is equal to 10 times RI. So RF must equal 100K. So based on that second requirement, RF must equal 100K. And then it's just a matter of going through this procedure again here. I'll just do it up here. Omega low pass equals 1 over RF CF, which implies that CF equals 1 over omega high pass, or omega low pass, sorry. Times RF. We know RF, we know omega low pass. This here equals 1 over 2 pi times 1.59 megahertz times 6 times 100K is equals 1.00 picofarads. Okay, we did it. We got all 4 component values. 10K, 100 nanofarads, 100K, 1 picofarad. So the real critical ones here, again, we can't change that, right? All we can do if we want to increase that is just cascade a bunch in the back to back. You're going to have to be given one of the component values. You're going to have to be. There'll be some indication. In this case, it was sort of sneakily told that RI is 10K. It's kind of given to you in a sort of roundabout way. From that point, once you know one of the resistors, this is going to tell you the other resistor, right? And then these frequencies are going to tell you the capacitors based on those frequencies and resistors. Yes?
How exactly did you get that omega high pass is equal to 1 by RF and CF, omega low pass is 1 by RF CF, no information?
Right here, omega low pass equals this?
No, on the top board, like from the equation of the transfer function.
From the equation, let me pull the board down so I can see exactly what you're doing. Are we still worrying about how we actually got to the nice form of the transfer function?
No. How did we get that omega high pass is equal to that and omega low pass is equal to that? Just from the equation, like how did you?
Oh, how do you know which one is the low pass and which one is the high pass?
Yeah.
Okay, that I can tell. That I can tell just from the components, from the way that the components look here. This capacitor is set up in series, so it's going to only allow high pass frequencies to pass through. Right. This one is set up in parallel, so it's going to only low frequencies are going to get through. High frequencies are going to be shorted out. So I don't know if that was an adequate explanation. Yeah, I guess that's a good answer. It's standard equations. This is the only way it's going to be configured. For this course, this is the only way it's going to be configured, right? If you wanted to actually get into it, you would have to look at it, like I said before, where you have ZF